In this video, I'll be teaching you everything you need to know about simple harmonic motion. Now, simple harmonic motion can be defined as a motion which has its acceleration directed towards a fixed point. In simple harmonic motion, there is to and fro movement, and it is a periodic motion, which means it occurs at regular time intervals. Now, what we usually use to describe simple harmonic motion is simple pendulum. So if I'm to sketch a diagram of a simple pendulum right here, this would be its position at equilibrium or at rest. Now, if it is slightly displaced to one side, so let's assume we raise this pendulum bulb down to the side and then release it, it's going to swing and swing to this other side, swing back again until it finally comes to rest. So that's a to and fro motion, and all these occur at regular time intervals. Don't mind my drawing, just using to make a representation. So the maximum displacement or the maximum distance from its equilibrium position is called its maximum displacement, and on a linear scale we can represent it like this. We call this the amplitude. All right, and this simple pendulum has its maximum velocity when it passes the center. So the maximum velocity is denoted as v. V is what, or you can just call it V max, or you can just write it as V. But maximum velocity is equals to the angular velocity times amplitude. We just got our formula 1, our first formula. And then not every time will the simple pendulum be displaced to its point of maximum displacement. Now, a pendulum can be displaced some meters away from its maximum displacement. As such, instead of us to have an amplitude that is the maximum displacement, we can have a distance somewhat x, what we call x, from the equilibrium position. And in such cases we use the formula v is equals to find the velocity, w square root a squared, that is the maximum displacement, minus x squared. So to find the velocity at a point if distance away from the equilibrium position, but not the maximum distance, we use this formula. So take note of it. And then we may be asked to calculate the energy of the simple harmonic motion. We just use our normal formula for kinetic energy, which is 1 over 2 Ka squared. Now K is a constant, or constant of proportionality, where we have F is equals to, where we have, if F is directly proportional to X, then F is going to be equals to Kx. So this is actually from Hooke's law, but can be applied to simple harmonic motion, because the force of the swinging pendulum is directly proportional to the displacement from its equilibrium position, and that's why we use this formula. So take note of it also. The kinetic energy, or the maximum kinetic energy, we use the amplitude 1 over 2k. Also, we can have cases where we are not given, or we are not given the amplitude, and we're just asked to find the energy of the simple harmonic motion. And we're given a speed of, or a velocity. We can just apply the normal formula for kinetic energy, which is 1 over 2 v squared. In place of v, we can also use w arrow, because v is equals to w arrow. So we can say w arrow squared, and this will give us 1 over 2 w squared arrow squared. Alright, for a swinging pendulum, this pendulum has a period. So the time taken for this pendulum to complete one oscillation is called its period. And the time for one oscillation is the time it takes the pendulum to swing from one end, that is from point A, to the other end, and then comes back to its starting position. So one to and fro motion constitutes one cycle in a simple pendulum, and the time taken to complete one cycle is called period. Now the formula for the period in simple pendulum is given by the equation period t is equals to 2 pi square root of L all over G, where L represents the length of the pendulum, G is acceleration due to gravity. Now there are cases where you might be given two different pendulums to calculate their change in length and those kind of stuff. Whenever you have such a case, you just have to use direct or indirect relationship. For this, we can see clearly that T is equals to, or rather directly proportional to, the square root of length. From this equation, I can see clearly that T is directly proportional to the square root of length. It is inversely proportional to acceleration due to gravity, right? It's inversely proportional to acceleration to gravity, square root of acceleration to gravity. What does this mean? It means that if we decrease the acceleration to gravity, the period of oscillation should increase. Are you following? So if we decrease acceleration to gravity, the period of oscillation should what? Should increase. Which means an object would oscillate slower on the moon, because the moon has lower acceleration due to gravity. I hope you understand. The longer the time of oscillation, the slower the oscillation. Alright, now this is not our primary focus. We're actually dependent on the length. So if period is directly proportional to the square root of length of a simple pendulum, it means that if the length is shorter, that is, if we decrease the length, if we decrease the length of this pendulum, the period should also decrease because it is directly proportional. So if you decrease length, the period decreases as well. And if you increase the length, the period increases as well. And if the period is decreasing, oscillation, that is the speed of oscillation, increases. Take note of that. All right, so now we can break this into two equations. T1 is equals to a constant k root L1, and we can also have T2 is equals to k root L2. We can even have as many as T3, T4, whichever your question demands of. Now we make this subject of formula. We have T1 all over root L1, and then we equate it to T2 all over root L2. So whenever you are given the initial period, initial length, and maybe they said they changed the length to a new length, then you should calculate the period. You can apply this formula. So another easy one you can use is, instead of saying t is directly proportional to square root of L, we can have t squared, that is, take the square of both sides. We can have t squared is equals to, or is directly proportional to L. And then we have T1 squared all over L1 is equals to T2 squared all over L2. This works as well. Well, some persons find it easier using this equation over this equation, because there's no square root in JAMB calculator, but you can easily just multiply two numbers together to get the square. So that's why this is more convenient for students. Now that we have talked about period in a simple pendulum, let's talk about simple harmonic motion in a spring. So spring SHM. Now, one thing I forgot to mention in simple pendulum is that the period or the oscillation of a simple pendulum is independent of its mass. In the formula for simple pendulum period, did you see mass in the equation? No. That means it is independent of the mass. So it does not matter how heavy the pendulum bob is, it will not affect the period of oscillation. That's what it means. But in the case of a spring, what am I drawing? In the case of a spring, it is dependent on the mass. So let's take this spring for example. And then attach a load of mass m. The length of this spring is given as L. Now, if we apply a force in this direction, this length is going to extend by a distance x, which means that force is directly proportional to the displacement x. So if we increase the applied force, that means the distance is going to increase. That's why we say this formula. This is gotten from Hooke's law. We can then simplify and say F is equals to kx, where k is constant of proportionality for the spring. Now, so I don't waste any more time, I'm just going to give you the formula directly without deriving. The period of oscillation of a spring is given by 2 pi root m all over the constant of proportionality. As you can see, the period of oscillation of a spring depends on the mass of the spring. We can still repeat the same thing we did in our previous case where we have T1, we can have T1 squared all over M1 is equals to T2 squared all over M2. This is for a spring. And lastly, I want to relate extension to acceleration due to gravity. Now, there is a shortcut formula and you might need it, so just take note of this formula. T is equals to 2 pi root E, which is extension, or let me just use x all over G. So this is another formula for the period of oscillation of a spring. How is this formula derived? Well, since we know that force is equals to kx, x where x is the extension, then force is also equals to mass times acceleration. The force here is the weight of the body, m, which is equivalent to weight mg, right? So we can replace force in the equation as mg is equals to kx, and then m over k is equals to x all over g. So m over k in this equation, we can just replace it with x over g, hence this equation.